Okay, this evening you have a treat. I have heard Ian's lecture on many occasions, and I still come back for more, as does he. And it's a wonderful experience here.
So serious, it's dangerous down there. The dangerous out here, but it's even worse than that. Now, just before I get started, just because there might be even stragglers that we've already had, but a piece of advice I was given many years ago, which has stood me in good stead, whether speaking in public or just everyday circumstances. It boils down to A, B, C, X, Y, Z. Always be courteous, examine your zip. On a slightly more serious note, the advice given to people speaking in public, given by many different people, is say what it is you're going to do, say it, and then say what you've done. I'll try to follow the advice. So what we're going to do tonight is we're going to have a look at two geometries. We're going to start with inversive geometry, and later on in the second half, that will be the conventional order for these halves to come, we'll have a look at projective geometry. It's a slightly idiosyncratic view. I'm the only person in the whole world who actually has it, but even so, it may be of some use. We'll see. At this point, it is conventional for the lecturer to say, don't take notes, there's a handout. Right? There is a handout, don't take notes, but the reason for not taking notes isn't that everything's in the handout. Actually, the handout doesn't have too much to do with the lecture at all, but then it's my endeavour to keep this lecture content-free. If I see anybody taking notes, could they pass them on to me at the end? And if I'm ever asked to give this lecture again, I'll take that content out. I'm going to start with something extremely boring. You carry on in the same line, but at least I'm admitting it's boring. The definition of inversion. Inversion in a circle says that the point is image P dashed if it lies on the same line as OP, and we have this condition on the length. The length OP times length OP dashed less than R squared. In other words, that product, OP dashed, is a constant. And since some of you have noticed there's something over there, it's not there just for decoration, it's not all that decorative. We have that illustration for you. Now, what this actually does is it shows that the product AEAC, after a whole lot of adding and subtracting and multiplying using Pythagoras, and if anybody really is interested, I'll leave it up for 10 seconds, but I really can't even want to follow it all the way through. It's just there to establish that AE times AC is AB squared minus BE squared. Now AB is that long line top left. Now that's a solid lump of wood over there. Can't be stretched or shrunk. BE is one of the shorter lines. Again, a solid lump of wood. Therefore, AB squared minus BE squared is a constant. It can be thought of as R squared for some R, but I don't care what that R is. Point about that is that E and C, that one are inverse points with respect to some circle, centre A over there. Now that's what this thing over here does. It sets up points and their inverses. Now, that's A, the centre of the inversion. That's E, the point whose inverse we're looking at. And that is C, the inverse point. What happens when I move this point round in a circle? The other end goes spinning round in a circle, and it goes in the opposite direction. I think that's right. There is better to come. Because whirling it round the top of our old ice cream carton isn't the only way of getting it to go in a circle. You can also use a radius, and I have here a radius. Right, now, see that radius? The circle described by that radius is going through the centre of the inversion. So I take point, and I move it in an arc of a circle which would pass through here if it could reach that far. Look at the other end. Shooting backwards and forwards along a line segment. Now the line that's there is just to help you, it's not actually the line it's following. But what I'm doing here is I'm creating a straight line segment. I know of no other way of creating a straight line segment. Pull a bit of string, it's got a bend in it. Take somebody's ruler, you're not going to trust somebody else's ruler. How can you get a straight line segment? You build yourself a Peaucellier inversor, you make sure that the circle you're going to describe here goes through the centre of the inversion, and the other end gives you a straight line segment. And that's made out of 4 smallish lumps of wood and 2 big lumps of wood. There's no measurement involved in it. All I need to know is that these 2 are the same size and those 4 are the same size. That was one of the problems that fascinated people for years. Peaucellier is reputed to have come up with that one. There's also one by an Englishman, Hart. Sometimes it's more elegant, but it's a great big clanking thing, so I don't use it. I have made one, it's quite difficult. Now, there's something I want to show you. There's something I want to show you. He didn't get to me again. He did something nasty last week. And I don't think he's stupid either. You know, 10 minutes ago, guess what? Good. What I have here is a demonstration using Projective Geometry. And what I'm going to do is I'm going to invert the red circle in the purpley circle, and the blue circle is the image of that. Now, if I take this circle and move it across, you see the image coming towards it, and when it reaches the inverted circle, we've got those points that stay fixed. As we keep on going, we eventually reach a very interesting case where the circle is its own image. That's when the inverting circle and the circle whose image I'm finding are orthogonal, and that's the one that crops up in our version of non-Euclidean geometry. If we keep on going, you see the image circle getting bigger and bigger and bigger, until eventually, when it goes through the centre of the inversion, it snaps into a straight line. Now it has to be a straight line, because if I go any further, it's curved the other way. If it's curved to the left there, it's curved to the right over here, it must be straight somewhere in the middle, and there it is. It sometimes looks somewhat different if we shrink that circle, give you a slightly different view of what happens. There are the straight lines outside. But that's quite nice. If anybody wants to try it for themselves, they can come down and have a shot. Now, let's forget the inversion for a while. I'm going to give you a problem that is given to us by, we believe, Jakob Steiner. Called Steiner's Chain problem. And we start with a circle inside another circle. Now, it's certainly possible to fit a circle into that grey area so that it touches the white circle on the inside and touches the big circle on the outside. And once I've put that circle in, I can find another circle that touches those 3. Show you the sort of thing. You can pop in one circle touching the inside one and the outside one. We can then pop in another one which touches the outside inside one and the first one I put in. At the next stage, I can put in another circle which touches the inside one, the outside one, and the last one I just put in. Now, the question about the chain is, can I keep going so that the last one touches the very first one? started in the wrong place? Maybe if I started somewhere else it would have worked. Maybe it's never going to work. I will leave that for the time being. Because I have another one. Smaller one. And I'm going to have a shot with this one. Now, is this one going to work? You know it's going to work, yes. And look, I've just gone through several minutes of tedium showing you one that didn't work. I know that crew, you know it's going to work. For all the wrong reasons, you've got no mathematical reason for it, but because you know how things go, you know it's going to work. It's like a little boy who had sat for a year in his science class and hadn't understood a word. And at the very end, the teacher of the class gathered round in front of him, and he took out a beaker of acid, he took out a pound coin, he said, I'm going to drop the pound coin into this beaker of acid, will it dissolve? And this little lad shouted out, no, no sir, no chance. And the teacher was dumbfounded, because he didn't think the kid had understood a word about acids. He said to him, why? How do you think it will dissolve? Your pound coin. Right, Good. Well, of course, you knew fine I was going to return to inversion eventually. I'd been shocked if I hadn't. It's a very special setup I've got here, and I've put the lengths in to show you what's going on. Now, the image lengths are kind of off the board there. It was very carefully arranged. Now, if you check on some distances, let's see, B dash, D dash, B dash, D dash, 2/3. So the image of that interval is going to be 2/3. C dash, D dash, 2/3. So the image of this interval is going to be 2/3. And A dash, C dash, A dash, C dash, 2/3. So the image of that one on the left is going to be 2/3. So they're all the same length. So that when we invert, we get that arrangement there. The ring in the middle, the circle in the middle, is the same width as the strip going round. Now, you've all seen that kind of arrangement before. Once you've got it into that shape, it's, I think, fairly straightforward to see. Doesn't mean that we can pack 6 circles round it. It's just a matter of symmetry there. Just symmetry, what am I saying? It's symmetry. Wonderful thing. But anyway, we've got the 6 circles packed in. And of course, what we do next is we invert back again. But even invert. What did I say about the reinverting the circle? Something like that anyway. And that's what happens. We've managed to get 6 circles packed in round our original one, where each in the chain touches the next one, so we get back to the very beginning. Now, when I was working on this, as you can see, it took an enormous amount of time and effort to get this. One night, I just left the computer running with this on. I was rather worried the next day when I discovered that not only did it have that, but some of its friends had visited. But to return to the original question, one of the original questions was, had I started in the wrong place? Or was it never going to work with the first one? Well, here is a demonstration of the answer to that. Now I've arranged it so that the circles on the right are being pulled round a little bit. The point is that wherever I had wanted to put my initial circle over on the left, I could have arranged for it to have an image of a circle over here. Then I could have fitted the other 5 round, inverted it back, and it would have worked. So, if you have this setup of one circle, another one inside it, not touching it, and you want to put in a chain of circles, it either works, and it works for everywhere you start, or it can't work at all. I don't know if there's money in it for anybody, but if I go on to try something, challenge people with an impossible one, and then when they give up, change it for a possible one and do it yourself. Now, that's enough of that for the time being. I want now to go into 3 dimensions. Well, there's usually a big cheer at this point. We're going on to 3 dimensions. And it's a similar kind of problem, although it has distinct differences. Now, this particular study comes from a man called Soddy. This is not fibbing. It's absolutely true. Soddy was a Nobel Prize winner for his work on isotopes, but we're more interested in his mathematics. And his puzzle was to do with this arrangement here. We have 3 touching spheres. Now, I would imagine that everybody knows that if you have 3 spheres and you take the 4th sphere, it'll touch all 3 of them. And once you've done that, if you look inside, there's space for a 5th sphere to fit in, touching all those 4. There's also another one goes around the outside, which I can't do because I can't show you this inside this. But once you put one in, you can then put another one in. So we start with these 3 and we put one in. Then we put in a second one. Then we'll put in a third one to touch the second one and these 3. And we'll keep on doing this, and we'll try to see if at the end of it we get a chain of these spheres going back so the first one touches the last one, the last one touches the first one. And with any luck, this apparatus will help to show what's going on. Now the problem is that the stuff I'm dealing with is quite small, so I'll try to show you under here, but I do want you to see what's going on. We're going to start with beat. Maybe just a little bit more like this one. Yeah. Starting with a wooden bead that size, like this, and I'm going to put it in, I'm actually going to put it in underneath. Now, it's not very colourful, but there it is underneath. What sort of sphere do you think I'm going to fit in that touches that wooden bead at the bottom and the 3 white beads? 3 white spheres. Very, very small. Well, it just, as they say, happens that I have one other small bead. Now, the reason I'm doing this under here is I want you to believe me. I am not cheating. I've gone to enormous trouble to get beads that actually touch. There it is. So, that's a rhetorical question, you're not going to make answer it. Now, that one doesn't quite reach the midpoint, or rather the mid-plane of the 3 spheres. So, if I'm going to fit one in that touches these 3 white ones and that spangly one in there, it's going to have to be pretty small. That's what I'm working out here. And there it is. Look at the front, can you hear that little click? It's touching. It's just touching no more. Another one, which fits neatly on there. Now, I know there are skeptics among you, but I think that's some sort of a demonstration that it's working. They're not falling out. And the reason they're not falling out is they're all touching. When I started on this business, I did a lot of calculations, and they do actually have to be pretty accurate with these because a very small difference in the sizes makes a huge difference later on. And I collected an enormous variety of various beads. I've got balls where you drop the bounce up the ceiling. I've got some where they hang together because they're magnetic. In desperation once, when I couldn't get a bead exactly the right size, I bought that. That is a gobstopper. Some of you are way ahead of me. What I intended to do is carry on until it was the right size. Fortunately, I managed to find one without that. Oh, close thing. Now, I've worked up from that wooden bead through 2 glass ones, not this rubber one on top. I now want to fit another sphere touching those 3 white spheres and that pink one. What sort of size of sphere are you expecting? Tennis ball, well, let's see. That's not far off being a tennis ball. So, a bit bigger. Almost that big. Yeah. Bigger? Yeah. Now, the folk at the front, you may not be totally convinced, but it's not very far, anyway. What about down at the bottom? We've usually dropped at least one by this thing. What about those 4? That wooden ball seems to come awful far up. What sort of sphere am I going to do now? Well, a bit bigger. It's not quite the Earth. It's a bit bigger than what I've had. So, let's see what we've got down here. As luck would have it, and it happens to there's one with a beach ball, especially imported from Canada. It was the only place I could get a beach ball this size. Lack of enterprise in Britain. Now remember, I'm trying to touch the wooden ball and the 3 white ones, and when I do it, now, that's not bad. I might be lying a little, but of course I'm not. The only thing that's in doubt is that these are a wee bit squashy, so if I'm not quite there, I can just push a wee bit harder. But essentially, what I've found is that 6 spheres have packed round. So the first one met up with the last one. Now, when I was doing the Steiner chain, I showed you one that didn't work first. To prove a point. This time I haven't shown you it not working. Is that just kindness on my part? Or was it just what was bound to happen? It's been a wee while since I mentioned inversion. Has to come into something. Oh dear, there goes the big bouncy ball. Oh! That's how well clear it was. That little bead didn't fall in. Now, I have here an inverting sphere, or at least all I can manage, because if I showed you the whole sphere, I wouldn't be able to fit this into it. It may look to you like the ball from a child's wheelbarrow. Well, once upon a time it was, but now it's an inverting sphere. What I'm going to do is I'm going to invert these 3 spheres in this. I'm going to do it in a special way. Right, now I want to hold it this way because it fits in what follows. I think you know, and certainly demonstrated, that if a circle goes through the center of the inverting circle, its image is a straight line. Right. If a sphere passes through the center of the inverting sphere, its image is going to be the 3-dimensional analog of a straight line. It's going to be a plane. That's one thing. The other thing is, we know that any points on the inverting circle stay put. So any points on the inverting sphere, which is this blue sphere here, any point on that is going to stay fixed. So we've got a ring of points, which are the points and their images. So the image has to be plane, and it's to be a plane that goes through that ring. So it's going to be a horizontal plane if I hold it like that. What about the image of this sphere? Don't need to go through the argument again. It's exactly the same. This goes through the center of the inverting sphere. Image is a plane, and what's more, it's a plane that goes through that ring. These 2 rings are parallel, so this plane is going to be parallel to that plane. So when we invert in this sphere, we're going to get a plane image of that, plane image of that, and of course we've got the lost one inside. It doesn't go through the center of the inverting sphere, it was off center a bit. So its image is going to be a sphere. That little sphere in there is tangential to these 2 spheres. So its image has to be tangential to the images of these two. Very long argument this, but very pretty. So, we're going to have a plane, and a plane as images, and the image of the sphere that's hidden in there is going to be another sphere, and it's going to be tangential to these two planes. Some of you may already have a picture in your mind of what that looks like. It's a little bit difficult to give a convincing illustration. The best I can manage is something like that. It's meant to show two planes, this sphere trapped between them. Now, if I try to pack spheres in this configuration so that the spheres touch the plane at the top, the plane at the bottom, and the one in the middle, it's going to be a bunch of spheres, all the same size, and in fact, you get that sort of thing. Again, you're familiar with the way spheres of the same size would sit in, say, a tennis ball box or something. What happens when I invert that? When I invert that back to this situation, I must get those 6 spheres in the ring, the green spheres, they must invert to a ring of spheres, touching each other and touching the inverse images of the plane and the plane. Now, this is a most startling result. It means that whatever 3 spheres I started with, 3 touching spheres, I must be able to start with any size of sphere I like, and then going round in a chain, eventually with 6 spheres, I'll get back to where I start. Always 6. If you try to do it in practice, you will find that there are problems. Sometimes the sphere you want to fit is one of these plane spheres, a sphere of 0 curvature, if you like. Or sometimes you find that you need a sphere that goes around the outside of the spheres you've already got, and that's almost impossible to do. In fact, you'll find that it's very difficult to get them actually to work practically. But nonetheless, in theory, it will always work with 6. And that's why this configuration is known as Soddy's Hexlet. Now, Soddy, I regret to say, did publish in Nature 1936, if you care to check it, some of his results on circles. And instead of calling them tangential circles, he called them kissing circles. Now, I think I'm going to hate myself for this. I looked at his work in Nature, and it was published in verse. I thought, what a wonderful thing for a summer school. Mathematics in verse. I don't have it with me, but I think it's engraved on my memory. One of the stanzas begins, 4 circles to the kissing come. The smaller is the benter. The bend is just the inverse of the distance from the center. You don't believe it? Nature, 1936, look up Soddy Frederick. It's there. But I decided I really couldn't inflict that on any audience, but it got the better of me. But that got me thinking. That's actually the end of what we're going to do in inversion. And I thought, verse, that would be nice in the middle. We can't really use all the, oh, put the verse up outside. Somebody last week said they thought that was good. I think his name was William McGonagall. But anyway, it inspired me to look for suitable verse for summer school, and I came up with this. There was a young lady from Crewe whose limerick stopped at line 2. However, I found another one which I thought was rather swish. There was a young man from Verdun the next thing is, it's actually slightly serious. Several years ago, I was having trouble sleeping, so I sat down in front of the television, the test match was on, and it worked. But And there on the screen, bottom of the screen, was Atherton 43 with a little asterisk or a star after it. And I didn't know what it meant. Now, there have been some cynics who said in the past they didn't believe this story because they don't believe Atherton ever reached 43, but it's not true. They said Atherton 43. And later on, I discovered what it meant. I should have known, but it meant 43 not out. But of course, they'd simply adopted our notation. Because our star Anybody in this audience who was in any risk of forgetting what our star meant now will never have any opportunity to forget it. To be of any use, a mnemonic must be rotten, and that passes. Okay, serious stuff again. Actually, I just want you to look at some pretty pictures to start with. It's a well-known kind of picture. You get them all over the place. I think this one is California, but for equally obvious show, you've seen almost exactly the same picture from both, and they exist elsewhere also. It's a picture of a road. Except, of course, what we're getting on the picture isn't a road at all, it's a big black triangle. But we know it's a road. We know its sides are marble. Yes, well, I have seen Roadrunner movies where the Roadrunner thought the one he was seeing was a road and it turned out to be a painting on a wall instead. But we know that that's actually a road. Next one. Slightly different. This is an architect's drawing of what was to be built. I think it's an airport in Japan, in fact, but that's irrelevant. It's a drawing of something that does not exist, or at least did not exist at the time. And yet, we know that we have a walkway on the right. We know that these beams along the top are parallel. From that drawing. The next one is one I've had many arguments about. It's a photograph of what I now know to be crepuscular rays. All right, what you see in the morning, early morning. It's not the very best of pictures, but it's very difficult to photograph. But what we've got are these beams of light, and they appear to converge somewhere above the picture. Now, what concerns me about this kind of picture is that I know that by the time the sun's rays reach us, they're pretty close to being parallel. Now, they're not exactly parallel, but there's not much of an angle between the rays. So how come we're seeing that? If you ask somebody to describe what they're seeing, if you happen to have the sun covered with a cloud, lots of mist around, and you see these rays shooting down, they'll say it looks like that. There was a French archaeologist camped in the plains of Giza, and one morning he looked out with the pyramids in the foreground, and he saw that in the distance. And he said immediately he was struck as to why the pyramids had to be the way they were. They were the equivalent in stone of this white pyramid. Now, is it a pyramid we're seeing? Or are we actually seeing parallel rays? In the other two pictures, we had lines that we said were parallel, although in the drawing they weren't, in the picture they were. I think those are essentially parallel, but I'm not sure. So the first one, we knew what was going on. And the second one, we constructed what was going on. And this time, there is some doubt. Now, this question of what is a parallel line is, well, let's just get this out of the road. This did appear in a textbook. It asked pupils, are those lines parallel? And the kids who thought, parallel lines are lines that do not meet, were prepared to say, yes, they're parallel. They're parallel because it didn't meet. They hadn't made the connection between line, or the distinction between line and line segments. Line segments don't meet. So they said they were parallel, and of course they were wrong, except, you see, they were actually right. Doesn't that disturb you? It's always disturbed me that something which wasn't parallel becomes parallel all of a sudden. Well, projective geometry is about that. Well, there's one other of my little funny slides. It's it's this one. Picture of a person who's actually campaigning on behalf of the homeless, and he's standing inside this square of buildings that were being left unlet in hope that the value would go up in time. And the point was being made that it could be used to house people. But I was intrigued by it as a photograph, because it's so striking, right, the way that the head is right in the middle. But then I started to look around the outside, and I became fairly convinced it was actually a composite photograph, that bits had been cobbled together. And to check it, I actually did a photocopy of it, and drew in pencil the lines which I'm now showing you on there. And if you look at them, you can see how they match up fairly well. Not very well centered, you can see the idea. And I was convinced that in fact these walls and the downpipes and so on were parallel. And the reason I was sure they were parallel, was I found the point where they met. Right. Last of the pretty pictures for the time being. Apart from the mucky marks on that glass there, can you tell what it is I drew? Oh, yeah, it's meant to be the cloud anyway. Why do we know it's a constellation? Why do we know it's a constellation? Of course, it's because the stars are close together. Right. Now, there is a serious point being made here. It is meaningful to say those stars are close together. We're not talking about distance. We're talking about what we see. We see those stars being close together because the light coming from those stars makes very small angles. Each ray makes a small angle the next one. So we see them close together. Proximity to us is not about how far away things are out there. It's how narrow the beam is when it reaches us, how small the angle is when it reaches us. And it's that kind of idea that leads to our construction of projective geometry. And that things that economies all pushed out. I want all the light I can get for this image. I would like it to be clear that there is to be no flash photography at this stage. I don't carry adequate insurance for this. I don't university has refused to add cover for me, so I'm afraid this is at the limit, and any disturbance just could be very serious indeed. I have when others try this. It didn't do it twice. I think he recovered. Now, I'm going to read that one later. See why I've moved everybody from the front row. Right. Projective geometry, in my opinion, is about, well, at least it starts with what we see. It's about our perception. So, when we're talking about where things are, it's a useful idea to have a coordinate system. That's the origin. Lovely subject this. Each of you can do this for yourself. You don't have to accept my origin, each of you can have your own. And we'll have that direction as the x-axis, that direction as the y-axis, which leaves me as the z-axis. A very good representation of the z-axis, I think you'd agree. Of length with no thickness. Got your attention. Right. What I want to concentrate on just now is there, at corner of the table. Now, in my coordinate system, the measurements are a bit crude, but essentially I want you to think of that as being half a unit that way, 1 unit that way, and 1.5 units that way. So its coordinates in R3 be a half, 1, negative 1.5. If I am stationary and I'm not using two eyes, just use the one, look at that. Unless I have other information, I have no way of telling where that point is in terms of its distance. All I know, and that's why I'm using this cane, all I know is that somewhere it's along that cane. So it could be at a half, 1, negative 1.5. Or it could be twice as far away. I don't know from up here. If all I can tell is that point is there, it's like the plough. When I look at the plough, I have no idea how far the stars are. I just know the direction. It's the same here. It might be 1, 2, negative 3, twice as far away. Or it could be half the distance. So when I look at something, all I know is where it is in terms of its direction. I need other information if I'm going to try to fit it into a distance away from it. Which is why we have this rather bizarre coordinate system that strikes people as being rather bizarre, where we use homogeneous coordinates. And there's the description of what I've just been talking about. We know that it's something like that because it's in that direction, but we don't know how far away it is, so we introduce this lambda. And once we've decided that we're going to use lambda there, we put square brackets in, and then we don't need to put in that it's multiple. The square brackets imply that any non-zero multiple would be the same point. In other words, would point in the same direction. Now, I do try to sell the message very strongly that projective geometry starts off with perception. That's a sensible kind of definition, but there is one very slightly awkward result of that definition. And that is, I said it was for any non-zero lambda. The ones down there are all positive. Suppose I had a negative value for lambda. Up there. Now, according to my way of thinking, I can still see it. I still see it's the same point, but now I'm seeing it at the back of my eye. Some people don't like that. I do. To remind you of that, I regret doing this. I have been told to do it. To remind you that projective geometry is about seeing, I have here an eye. To remind you what kind of sight it is, it's a projective eye. It sees out the back and the front at the same time and doesn't know which. It recognizes front and back as being the same. Just very slightly an extension of our ordinary meanings of words. Just a teensy bit. Now, what does this imply about lines? We're going to call points with capital P's. Now, there's a problem with how you say this. You can say the projective points. Nice and straightforward, rather long-winded. We call them P-points. Some people like. Or you can just make it clear that it's a capital P you're using. Become points. You have somebody you don't like in front of you, so much the better. Now, what you see as a line in free space along there, if I'm looking at it, what we get is a great big sheet, and that sheet comes edgeways into my eye. So that's why the lines with a capital L in projective geometry are represented by planes going through the origin. They're sheets which we see edge on, and therefore we see them as lines. That's fine. What about when two lines intersect? Well, the line down the edge of the bench there, and the other one along the end, there's a projective line going along there. And that's this sheet. There's a projective line along there, another sheet, and they meet along a ray going through my eye, so they're meeting at a projective point. I will see a line meeting a line at a point. That's fine, that's just what we expect. The nice thing about projective geometry is that it deals with another case. And just before going on to that, I want to make clear what's been going on. Once I have the system of rays there, they're representing what I see. But I don't know where I'm seeing them. I believe they're on a plane somewhere. We'll stick with the planes now. But I don't know which plane. If I knew they were on that plane, then it'd be ordinary geometry again. But from where I stand, all I'm aware of is direction. So I don't know where the plane is. So what we do is, to get our movements in this geometry, we start with a configuration on a plane, we set up the projective rays, and then we chop across to another plane, because that would equally well represent what we're seeing. You're then entitled to move that around, do the same thing all over again, set up another system of rays, chop across it. Now doing it once is called taking a perspectivity, and if you do a sequence, you get projective transformations. Right, well, that's a mouthful. You see that edge and that edge as being parallel. You believe they are. Actually, you're not seeing them parallel. You're using information you already have to deduce that they're parallel. But we'll believe they're parallel. Now, what happens when I look along them? See that angle getting smaller? That means that these points are getting closer. Genuinely. What about the actual projective lines? Remember, this projective line was a sheet. You can see it being swept out. It could equally well be thought of as a sheet. It just comes up, goes through my eye. And this one comes up, it goes through my eye. So it's like a rooftop. You go up and you meet along the ridge at the top. And that's a perfectly good projective point. The problem is, it doesn't represent anything on that plane. That's when it's called an ideal point. It's a perfectly good projective point. It's ideal as far as that plane is concerned. If, however, I drop another embedding plane in, and I drop it in across this, then that point just becomes an ordinary point. Nothing special about it, it's not ideal anymore. And that helps to explain what I feel is a paradox about the very first picture, the road, which appears to us as a big black triangle, but we believe is actually a road with parallel sides. We wouldn't be a lot of use to this otherwise. Now, that point where the sides meet, in the picture, those sides do most definitely meet. That point is a perfectly ordinary point in the embedding plane of our photograph. It's an ideal point as far as the plane the road is in. Now, projective geometry, like most areas of mathematics it seems, has its fundamental theorem. There we are. This is almost what it says in the handbook. There's only one slight difference. My spelling has changed just a, well, actually, I suppose it's my punctuation has changed just a little bit. If you're going to call lines with a capital L, I don't see why it should be changed to a small L just when it's in the middle of a word. So, any 4 points, no 3 of which are collinear, can be mapped to any 4 points, no 3 of which are collinear. Awful meaningful stuff, that. Well, I remember a whole bunch of us sitting around trying to interpret this, because we knew that projective geometry was about perspective. We knew it was about drawing things, offing them, having a look at them, putting new planes across, and seeing what you had. But what troubled us was this problem. Suppose you consider 3 of the points as forming a triangle and the 4th one inside. Not worried about what shape the triangle is, what size the triangle is. Just 3 points with 1 other point inside. And afterwards, we're supposed to have the 3 points with a point outside. Now, if you try drawing a triangle and you put a point inside it, and you hold that bit of paper up, and you turn it round, the triangle changes shape, the point stays in. Turn it the other way, point stays. On transparent paper, you turn it over, point still in. Looking at the edgeways on doesn't do a lot of good, because you lose everything that way. So, what was going on? How could the fundamental theorem of projective geometry be true? How could we get these funny diagrams? Some of you have commented on the fact that you get TNA questions with drawings where you've got 1, 0, 0 over there, 1, 1, 1 over here, 0, 1, 0 here, 0, 0, 1 there, and it's very difficult to see how it's possible. Well, eventually we discovered what we had to do. What we had to do was we had to go to our local home base, and we had to persuade the people there to give us free rein with their bamboo sticks collection until we had 4 really beautifully shaped canes. this stage you can always talk on yourself, or I'm just waiting for you to put this. I love this word. Reminds me of the days of the mods. Can you see yourself with your scooter and all this? That's a serious purpose, so it's such fun. Now, the obvious way to set up a triangle with one point inside it was to have an equilateral. I don't juggle, just in case you're no gimmicks in this business. The obvious thing was to draw our triangle with one point along the x-axis, 1, 0, 0, one along the y-axis at 0, 1, 0, one on the z-axis at 0, 0, 1. Now that defines our plane, and I want to put the fourth one, the dot on the inside, on 1, 1, 1. There we go, unit point, 1, 1, 1. Now, I think I've done reasonably well what I said. Over here, in the triangle with 3 yellow balls, the red one inside. Everybody agree about that? Now, see, what we were trying to do was we were trying to drop in a plane like that. And we were able to shift these points way along, so instead of it being equilateral, it was isosceles, and this point moved along as well, but it still stayed inside the triangle. And no matter what we did, that point stayed stubbornly inside the triangle. There may be sophisticates among you who have figured out what it took us so long to figure out, how we put in an embedding plane so that that point is outside the triangle of the other 3. Good. Nobody's actually shouting out. If you take a plane that comes down from here, it's that one first, there, then comes down, cuts this ray, back here a bit, and we cut this ray, y-axis, here a bit. And where does that plane cut? The z-axis, coming down, there. Must be somewhere below the origin. Is it down there somewhere? No. Not sure what was in that plane. That's the idea. Somewhere down there, there's a point. Now, see? It's outside the triangle. How did we manage this trick when we couldn't do it before? Well, the reason is because our eye is there, and it's looking forward at that point, forward at that point, forward at that point, and backwards at that point. It's not one we can actually do. It's in the geometry. This is an illustration of why, having seen how projective geometry works, you stop doing this. Please, let's not have anybody, when you come to do your projective geometry, say, could you bring those keys along and set up this? I want to work out what it looks like. It's futile. You really just can't do it. But nonetheless, that's where it started. It started with our perception. Now, there was one other thing which I think was fascinating in projective geometry. And that's to do with conic sections. And you know the trouble we've had with the equations of the various conic sections, how to distinguish a hyperbola from an ellipse from a parabola. And then there are the degenerate ones, which we don't speak about them. But the non-degenerate conic sections are a pain in the neck in ordinary geometry. And we're told that in projective geometry, the conic sections are all the same. That one conic can be mapped to another conic. Now, I've seen the diagrams in the book, and they're very good. I just didn't believe them. I wanted to understand myself. How was it possible for the hyperbola, which is quite clearly in 2 bits, one over there, one over there, how was it possible for that to become an ellipse? I could always believe the parabola becoming an ellipse, always. But the hyperbola, nah, it's doing a fast one there. Well, it just so happens that I have a small example of a hyperbole here. Well, it's as near as I could manage. It's not easy to draw an hyperbola this size. And now I want to go through my recipe as to how you transform one projective figure into another one. You draw it on an embedded plane, you set up the system of rays, and then you cut across that system of rays with another embedding plane. And the two drawings are equivalent, one that was on the original plane and the one on the embedding plane. Right, well, this is why, now if I'm getting too close to shit. Oh, I forgot to check the projector. Oh. So here we go. Remember, my eye is the center. That's the origin. So, set up the rays by looking along there, come round, keep on coming round. There's a way out there, and so eventually, we're level with the board, flat with the board, parallel. We've actually reached the asymptote. It's an ideal point. But it's an ideal point over on my left. It's also an ideal point over on my right. It's become that branch. Keep on going round. The same the other way. And we reach the other asymptote. Well, at least we're parallel to our asymptote. We found a second projective point, which is an ideal point. And it's ideal for that. It's ideal in both directions at the same time, so it's joined it up. Now, if I do that again, try to imagine an embedding plane across here, coming straight out from the board, and try to imagine the shape that's on it. Now, it's pretty wide, but it's certainly joined up. It may be, well, it is an ellipse, in fact, if I'm doing this accurately. We might be prepared to believe that it's an ellipse. We've certainly managed to take two distinct branches and join them. So it does make sense after all. I believe them now. It's a good one. Now, some time ago, I said there were three things I could do. And the last one was I could tell you what it is we've done. We're finished.